Newton's second law of motion is used in kinetics of particles. Here are some examples to show the procedure. Welcome to dynamics of rigid bodies. This scenario is of a car which was placed to a total stop from an initial speed of 120 kph in a distance of 50 meters during a brake test. All four wheels contribute equally to the braking force. Determine the braking force at each wheel assuming a constant acceleration to the 1,600 kilogram car. At point 1, the velocity is 120 kilometers per hour, and it has fully stopped at point 2. Newton's law states that the net force is the product of the mass of the particle and its acceleration, and this can be rewritten as the four wheels braking force as equal to the car's mass of 1,600 kilograms times acceleration. First is to convert the initial velocity of 120 kph into meters per second, and that is by multiplying it with 100 meters and dividing the answer with 3,600 seconds to yield 100 over 3 or 33.33 meters per second. With the given, use the motion formula consisting of the square of the final velocity as equal to the square of the initial velocity less twice of acceleration with the distance. Plugging in the values, we have 0 is the square of 33.33 minus twice of a times 50, which can be simplified as 100a equal to 10,000 all over 9, which makes the acceleration equal to 100 over 9 or 11.11 meters per square second. Place the value of acceleration into Newton's formula to get 4,444.44 kilogram meter per square second, also known as Newton. The second case is to have the same scenario move along a 10-degree incline where the surface has a frictional coefficient of 0.20. Having the same scene, the initial velocity in kph is then converted into meters per second, and that's 33.33 meters per second. With the same motion formula, 0 is the square of 33.33 minus 2a times 50 meters, simplified further as 11.11 meters per square second. With Newton's formula, F is equal to m times a. Force is considered as the force of the four wheels less the friction, and this is equated to the mass of 1,600 times acceleration. Friction is computed as the coefficient times the normal force, where the normal force is also dependent on the weight. Take the car inclined at 10 degrees. Its weight is still projected vertically downward as 1,600 kilograms times g of 9.81 meters per square second, giving 15,696 newtons. The normal force is taken from the weight but perpendicular to the surface, so it is taken as the weight of 15,696 times cosine of 10 degrees, resulting to 15,457.54 newtons. Friction as mu times normal force is computed as 0.20 times 15,457.54 newtons to have 3,091.51 newtons. Plug this into the general formula to make it 4F less 3091.51 is equal to 1600 times 100 all over 9 to have 5217.32 newtons. If a lighter car is used in the brake test and it moves slower at 100 kph, which stopped after running a distance of 60 meters, let's check the difference in the braking force of each wheel. Just the same as the previous example, convert the velocity into meters per second, giving 250 all over 9 meters per second. Use this into the motion formula of the square final velocity as equal to the square of the initial velocity less twice of the acceleration times distance s, which gives the acceleration as 6.43 meters per square second. Now that we have A, we can complete Newton's formula to have the braking force in each wheel as 2250.51 newtons. Let's take the second scene into an incline of 15 degrees and place a coefficient of friction for the surface equal to 0.25. Take note that regardless what the surface is, the motion formula will still consider a straight path, so we take the initial velocity as 100 kph converted into 27.78 meters per second, and plug these into the motion formula where acceleration comes out as 6.43 meters per square second. Take note that this is the same value we solved earlier for a horizontal surface. The final velocity still is 0 as the car already stopped at a distance of 60 meters. We move on to the general equation of F equal to m times A, where the net force is taken as the force on each wheel less the frictional force. Furthermore, small f or the frictional force is solved as mu times the normal force. That is why we need to find the normal force, which is dependent on the weight. Weight, on the other hand, is taken as 1,400 kilograms times the gravitational acceleration of 9.81, giving 13,734 newtons directed vertically downwards. The normal force is derived from this, although it is applied perpendicularly to the surface. Thus, N is 13,734 times cosine of 15 degrees, giving 13,266.03 newtons. We can now solve for the small f from 0.25 times 13,266.03, which results to 3,316.51 newtons. This value is then placed into the general equation to have 4 times the braking force of each wheel less 3,316.51, and this is equated to 1,400 kilograms times the acceleration of 6.43, where 4F turns out as 12,318.57 newtons, bringing the braking force for each wheel as 3,079.64 newtons.